Hello, everyone. What I want to do in this video is prove that step functions are dense in LP. We're just going to focus on P between 1 and infinity. And we'll put that to really good use and prove a very, very classical result in Fourier analysis called the Riemann-Lebesgue lemma. And I'll describe intuitively what's going on. Yeah, I'll explain exactly what I mean by a step function. So the key to proving that step functions are dense in LP is the following little proposition. This is in Royden actually quite early on. I guess it's really a lemma because we're going to use it for this purpose, proving step functions are dense in LP. But yeah, I just don't think there's a point in going through it early on when you basically don't use it for anything other than this. I'll kind of explain why this is useful in a minute. Okay, so let's say A is a subset of R and it's measurable with finite measure. So the claim is for any epsilon bigger than 0, there exists open finite intervals so these are finite intervals, finite open intervals, and there's a finite number of them, where if theta is this open, disjoint. These are disjoint. Important. Then the measure of this here, which remember is all the stuff in the union, take away the intersection. So I'll just remind you of what this is. Remember, this here is theta take away A, disjoint union, A take away theta. So this is less than epsilon. Okay. And for some reason, I'm having a brain fart on what this operation is called, classical set theoretical operation. But anyway, yeah, so it's the kind of picture, it's the obvious thing. I'll even put this in yellow. So let's say this is theta, this is A. Move this over a bit. Let's say theta A. All right. Yeah, so it's just going to be theta take away A and A take away theta. So it's a union take away the intersection. So this is theta again, whatever this is. Okay. Right, so let me prove this and then we'll put this to good use. So we're actually going to need this to take the LP norm of the difference of two characteristic functions. That's where the set operation really comes into play. But yeah, so like I said, this is proved early on in the book. It really uses stuff done a long time ago, but anyway. All right, so I'm first going to use outer outer regularity. That's the first thing to do. So pick open U containing A, almost throw E there, where this is less than less than epsilon. It might need epsilon over 2, but whatever. Okay, so first of all, the fact that A has finite measure tells us that U has to have finite measure. Why? Well, very simply, because A is measurable, finite measure, it's going to be U take away A, this measure of U minus measure of A. This is less than epsilon. And I don't really care that this is less than the measure of A plus epsilon. What I care about is, well, this is finite. Epsilon represents something small, so obviously this is finite. Okay. So the measure of U is finite. Okay, so that's good. It's very good. Why? Well, remember, I don't think we proved this in the video. I know in lecture I don't prove it, but maybe I proved it in one of the videos. I know I mentioned it. So I'm going to write U as the disjoint union of an infinite number, possibly infinite number of open intervals. So key observation here is both AI and BI are real numbers for every I. Very simply, because the measure of U is finite. Right? Yeah, so the measure of U is finite. So if any of these was minus infinity or plus infinity, well, the measure of U would be infinite. So each one of these, so it'd be clear, each one of these is a real number. Okay, yeah, so it's actually pretty easy proof. Right, so yeah, these are finite intervals, finite disjoint intervals. Okay. Sorry, I use J, so I'll use J here. Not that it really matters much, but it should be a little consistent. Okay, let's use this fact here one more time. All right, just a little baby measure theory, should be very easy by this point, what we're doing. So this here is the measure of U. Because these are disjoint, this is a disjoint union, countable disjoint union, and this is finite. Okay. Right, so what do we need to do? So I need to pick N where this sum n plus 1 to infinity. So the tail of a convergent sum always converges to 0 as we go further in a tail. So this can be made less than epsilon. Right. Okay, so that's useful. Yeah, so why is that useful? Because that means this sum here well, obviously, remember this here equals the infinite sum. Yeah, so this equals the infinite sum, so this is less than epsilon. J equals n plus 1 infinity. Okay, so yeah, we're almost done. So that means I can set theta to be this disjoint union of open finite intervals. Right. So clearly, this is U is a whole union. So this is definitely a subset of U. That's going to be useful. Right. Okay, so one thing to observe is that this here, let me do it in yellow, this. So this here equals the measure of theta take away A plus the measure of A take away theta. So we're going to estimate these two right now. It'll be pretty easy to do. I think I'll get 2 epsilon, whatever. So let's actually make it epsilon over 2. Have a snob like that. So, yeah. Okay. Yeah. So, well, this one is easy because theta is a subset of U. So this is less than or equal to U take away A, the measure of U take away A. And that's less than epsilon over 2. While on the other hand, so remember that A is a subset of U. So that means the measure of A take away theta is less than or equal to the measure of U take away theta equals the measure of U minus the measure of theta. I guess I technically didn't need to do all this, but I already did it. So yeah, so just like here, this is blue here. So this is the measure of theta, because theta is this disjoint union. So we already have it here. The measure of U minus the measure of theta is less than epsilon over 2. It's exactly what we just had a second ago. So conclusion. Just from here, both of these are less than epsilon over 2. This here is less than epsilon. Okay, so what is the point of what we just proved? Well, the point is as follows. So for any epsilon, let's say A has finite measure and theta is as before. Okay. So what I have here really works for any two subsets of the real line whatsoever, but that's not very important, I would say, in general. Just thinking this is doing this with just two arbitrary subsets. Yeah, so let's look at this difference here of characteristic functions, absolute value. So this is, well, I claim it's 1 if x is in the symmetric difference of theta and A. And I forgot before what this was. It's called the symmetric difference. And just a reminder, this is theta we take away A, this joint union, A take away theta. Right. And so why is this true? Well, if x is in theta but not in A, then it's 1 minus 0, absolute value is 1. If x is in A but not in theta, then its absolute value of 0 minus 1 is still 1. On the other hand, if x is not in theta nor in A, then 0 minus 0 is 0. If x is in the intersection, then it's 1 minus 1 is 0. So otherwise it's 0. So this is simply a characteristic function of theta symmetric difference A. And what we're particularly interested in is, well, raising it to the p, and that does nothing here because it's 0 or 1. All right, so again, for any epsilon, let's say theta is this finite disjoint union of finite open intervals where A has measure less than infinity. So taking the LP norm of the difference of characteristic functions, well, LP norm raised to the P, this is simply, well, the measure of the symmetric difference. And this is less than epsilon. Okay. So given any set A, a finite measure, I can approximate the characteristic function of A in the LP norm by the characteristic function of theta for some theta that is the finite disjoint union of finite open intervals. That's the point. And we'll put this to good use in proving the following results. Okay. So a little definition. Let's say S is an LP. It's a definition you're probably familiar with. So we say S is dense if for any epsilon bigger than 0 and F in LP, there exists G in LP, G in S, where this here is less than epsilon. So I can approximate in the LP norm anything in LP by stuff in S to any arbitrary degree, basically. That's what we're saying. Okay. So the theorem is as follows. So if S is the set of all step functions, what is a step function? It's a linear combination of characteristic functions. These could be complex. So it's a finite linear combination of characteristic functions of open intervals where each of these is finite. It's a finite open. Each of these is a finite open interval. Obviously, this is a subset of LP. So the claim is that this is dense in LP. And a very easy consequence of this literally takes like a few minutes to prove if you have this theorem on your belt, is the Riemann-Lebesgue lemma, very important basic result in Fourier analysis. You can prove the Riemann-Lebesgue lemma very easily from this theorem. Okay, so to prove the theorem, I need a little lemma. And this lemma works in an arbitrary metric space. And this is basically the metric space definition of density. So nothing special here. It's a definition you're probably familiar with. Okay. Let's suppose that we have a nested sequence of subsets of LP. I think I'll stop writing of R. It's just annoying. But again, this really works for any base metric space and having a nested sequence of metric spaces. So here SI is dense and SI minus 1 for each I equals 1 to n. Then the claim is Sn is dense in LP. It's a pretty obvious kind of thing, pretty easy thing to prove, nothing too surprising. All right, so for the purposes of the proof, let's just call this S0. That's just going to make the proof a little cleaner. So I'm defining S0 to be LP. Let's say epsilon is bigger than 0. Let's say F is an LP, and again, this is S0, defining it to be S0. All right. Okay, so pick F1 and S1. S1 is dense in LP. All right, so let's just call this F0 again to make the proof a little. So I'm defining F0 to just be F. All right. Here I'm just simply doing density of S1 and LP. Well, S2 is dense in S1, so you kind of get the idea. Right. So for each I, 1 through n, pick F pick Fi in S I, where Fi minus 1, difference of that in the LP norm is less than epsilon over n. So basically, No, F0 is an S0. F1 is an S1. So in general, Fi is an Si. So Fi minus 1 is an Si minus 1. Si is dense and Si minus 1. So we can always do this. Now this is easy triangle inequality. Again, just remember, make this proof a little easier notation-wise. We designate this to be F0. So this is going to be the j equals 1 to n. So this is a telescoping sum. You want to check this yourself by all means, but it is definitely going to be telescoping. Write out basically a bunch of terms. You'll see this. It's Fi minus F minus 1. So by the triangle inequality, really Minkowski's inequality, less than or equal to the sum and that's less than n, sum up epsilon over n times, we get epsilon. Each one of these is less than epsilon over. So very, very, very easy little results, just to make the proof basically a little cleaner. Okay, so the proof of this theorem. Let's say F is an LP. So let's do step 1. So basically, I'm going to use the lemma with n equals 3, actually. That's really all we need. Okay, so if Fn is this characteristic function, okay. So one thing I want to do, I don't want to write anything, but what I'm going to do is, so F is an LP. So it is finite almost everywhere. So I want to redefine F to be 0 where it was originally plus or minus infinity. Or where either the real or complex part, rather, is plus or minus infinity. Okay? So that means I'm redefining F on a set of measure 0, so it does not affect integration whatsoever. So I'm just going to assume F is a real value or complex value, genuinely complex valued on all the real. Right? That just means I'm redefining F to be 0 on a set possibly of measure 0. Or on a set of measure 0, possibly. When I say possibly, I might not even have to redefine it at all. But at worst, I'm redefining it to be 0 on a set of measure 0. All right, so this is important because if I want to take the difference here, then this is just going to be characteristic function of R, take away this interval. So I want this to the P, to raise to the P, and this is obvious because if X is away, sorry, if X is in the interval minus n to n, then Fn is F. So you're just taking F minus F, that's well defined. F, we're assuming, is complex valued everywhere. So it's just 0. F minus F is 0. But away from minus n to n, Fn is 0, so it's just absolute value of minus F, which is absolute value of F to the P. Okay. Also, this says well, this is a denominator for all of these. So by the Lebesgue-Damier convergence theorem, this limit equals 0 All right, so what have we actually proved? So if S1 is set of all F, I'll stop writing LP of R. So set of all F and LP such that F equals characteristic function of minus n to n of F for some n. Then S1 is dense in LP. Right? We explicitly just shown that we can approximate F, or F is the limit of Fn in LP, and Fn equals the characteristic function of minus n to n times Fn. You multiply Fn by the characteristic function of minus n to n. You're just literally multiplying the characteristic function of the same set twice, which has no effect. So Fn, each Fn is in this set here, right? So this is dense, right? So now let's go to step 2. Okay. So if F is an S1 and F is U plus IV, then by a simple approximation lemma, pick simple var phi n and psi n. So we have this pointwise. And we can assume by a simple approximation lemma that this is true. So this is always true. The absolute value of the real part is always less than or equal to the absolute value of the whole complex number. Okay, so what this says is, thanks to the simple approximation lemma, so let's say Fn tilde is var phi n plus I psi n. So again, by the Lebesgue-Dominier convergence theorem, because we have pointwise convergence on R, we have convergence in LP. Again, by the Lebesgue-Dominier convergence theorem. Yeah, so the dominator here would be absolute 2 to the p, absolute value of f to the p, maybe 4 to the p, absolute value of f to the p, but basically the same kind of thing, because each one of these is dominated by absolute value of f. The dominator is pretty trivial, just like before. All right. Okay. But the key thing to understand is this is less than or equal to f, and this is characteristic function of minus n to n for some big N. Same thing for psi. Okay, so that means this equals 0 on R take away minus n to n. Same thing for psi. Because simply if we're away from minus n to n, then this is 0. So if we're away from minus n to n, these two that I'm circling are 0. And so, well, absolute value of var phi n is less than or equal to 0, so it's got to be 0. So that implies that not only is this a simple function, but this has a property that I want from before. For this n, f tilde n is this characteristic function times f tilde n, simply because, well, again, if we're away from minus n to n, these are all 0. So fn tilde is 0 away from minus n to n. Sorry. So we just proved that both of these are 0 on R take away minus n to n. So that means this Fn has to be 0 on R take away minus n to n. Well, this is also 0 on R take away minus n to n. So they're both 0 on R take away minus n to n. And on minus n to n, they're obviously equal. Okay, okay, so what have we proved? We have proved the following. So Fn tilde is in all this collection of simple functions on R such that f equals this here okay, and let's say this is S2. Okay, so S2 is dense in S1. That is exactly what we have just proved, and I really need to plug in my laptop before it dies, so just bear with me a moment. But yeah, we just proved that S2 is dense in S1. Now we're basically almost done. I mean, we're basically done now. Okay, so the third step. Okay, so first of all, if f is an S2, f equals, it's a step function. So let's write it. Doesn't matter how the hell I write it. Say I equals 1 to j, ci characteristic function of e I. Okay, so what does this mean? So take this, multiply it by this characteristic function. Well, you could just distribute this inside and when you multiply characteristic functions, that has the effect of taking intersections, characteristic function of the intersection. So that means f actually, and this is really what's crucial, to use the result we started the video off with. So in other words, f is really a special simple function. It's a simple function with each of these having finite measure. I mean, the measure is at most 2n. All right. Okay, so let's yeah, so get the point here. So let's write this as I equals 1 j ci ei tilde again, I don't really care what this is. The point is that's important that this is finite, has finite measure. Okay. Right. So one thing without loss of generality. So right, just going back, where's the theorem? So actually, yeah, let me to fit this into that little lemma, let's say this is S3. So I need to prove S2 is dense in S3. That's my goal. And if I do that by the lemma, I am done. Because S1 is dense in LP, S2 is dense in L1. I need to prove S3 is dense in S2. If I can do that, S3 is dense in LP. So we picked something in S2, right? I need to approximate it by something in S3. Okay, so yeah, if all the CIs are 0, then F already is an S3. Basically, I don't care what intervals you pick, just set all the coefficients to be 0. So yeah, what I'm saying is trivially, the 0 function is an S3. Right? Set all the coefficients to be 0. So if M is this max, I don't even remember what I do, J. Yeah, so then F is an S3. So assume M is positive. Okay, so for each EI tilde, pick theta I. So I'll write it like this. This is the disjoint union. So So I guess I'm really doing this for each I, so k equals 1 to Li. So A right. And each of these are finite. Right. So pick theta I, where this here is less than epsilon over what works, J over M. So if the F tilde is going to be the sum here, I equals 1 to J, Ci characteristic function of theta I, and this is certainly in S3. This is certainly the finite linear combination of the characteristic function of open finite intervals. F tilde is definitely the a finite linear combination of finite linear combination of the characteristic function of finite open intervals, and thus F tilde is certainly a step function. So explicitly, you can write this as a little silly, but maybe to make that clearer. K equals 1 to Li, Ci characteristic function, A Ki Bki. Simply because each one of these, because this is disjoint, this is going to be the sum K equals 1 to Li, Aki Bki. A lot of commas here, but you get the point. Okay, right, so yeah, so in this case, F minus F tilde. I'm gonna be a little too quick here. So this is going to be, I mean, this is kind of odd. This is basically trivial now, but I equals 1 to J, Ci, character's function of EI tilde minus I equals 1 to J, Ci, theta I, LP. So by triangle inequality, this is less than or equal to I equals 1 to J, absolute value of Ci, times the difference of these characteristic functions. And as I said, this is really the heart of the proof. Well, this is less than epsilon. We picked this to be less than epsilon over Jn. Right. So yeah, we're done. We have proved that, by definition, really, S3 is dense in S2. So I want to finish off this video with two useful corollaries of what we just proved. And actually the last corollary, we essentially was basically one step in the proof of the density of step functions. And we could have just separated that itself. And that's basically the density of simple functions in LP. But anyway, so yeah, corollary, and this is easy stuff, but useful stuff, particularly so you don't have to repeat this over and over again. So let's say E is measurable as usual. Could have finite or infinite measure, doesn't matter. And let's say SE for all sort of step functions on E. What do I mean by that? Kind of the obvious thing. The only kind of thing it could be, which is just like step functions or intersect E. Right, so all linear combinations of step functions where my intervals are intersecting E. Right. Okay, then SE is dense and LP of E. And again, the proof technically works with a little tiny bit of modification for P between 0 and 1, for all P between 0 and infinity, but we're just really considering P between 1 and infinity. So P between 0 and 1 is, I would say it's relatively obscure in that, and if a textbook uses LP for P between 0 and 1, they'll often say, oh, you can go back, they'll kind of like remind you, even very advanced books, like, oh, hey, go back to your real analysis book and all these proofs work for P between 0 and 1. And they remind you of that because most of these books just, well, let's assume P is between 1 and infinity. We don't even want to look at 0 to 1. But yeah, the proof is pretty easy. So let's say G is an LPE. So I'm going to cook up something in a trivial way that's an LP of R. So it's G on E, 0 on E complement. Basically, it's G times a characteristic function of E, but I think this is a little clearer to write it. So trivially, we have G tilde is going to be, G is going to be the characteristic function of E, G tilde on E, because G equals, G equals G tilde on E. It's absolutely trivial. Yeah. So, yeah, and trivially, actually, the LP norm of G tilde on R is going to be the LP norm of G on E. That's kind of trivial because it's 0 away from E, G tilde. All right. Yeah, so by density of step functions in L P of R, I will pick F tilde. Let's say it's J equals 1 to N. CJ characteristic function, AJ, BJ, where these are real numbers. AJ is obviously less than BJ, but they're both real numbers. Right, so we're basically done. So setting F to be F tilde times characteristic function of E, which of course, when you multiply by a characteristic function of E, turns into intersections because you're multiplying these two characteristic functions. Yeah, you're going to be multiplying these two characteristic functions together. So this is going to be CJ so this is an SE. That. So yeah, you have F minus G L P E. Just write the definition. Yeah, and F of course equals F tilde on E. Or in other words, well, by definition, F is F tilde, the characteristic function of E. So this is characteristic function of E, F tilde. We commented before that G is a characteristic function of E, G tilde. All right, so what you could do is simply say that this is going to be equal to, so of course these are equal F tilde, G tilde, so tilde, G tilde, and this is less than or equal to replacing E with the real line. So G tilde is going to be 0 away from E, but there's no reason, and this is why this is not hard, but it requires a proof. There's no reason why F tilde is 0 away from F tilde. Yeah, there's no reason why F tilde necessarily is 0 away from E. Right? But it's okay. Everything's non-negative, so you can replace E with R, and you get less than or equal to tilde minus G tilde. And that's epsilon, because this equals this is F tilde minus G tilde LP. And we pick this to be epsilon. Right. So that finishes the proof. An immediate corollary is as follows. Yeah, and the corollary is it's absolutely immediate. Simple functions on E are dense and LP of E. Right. And well, that just follows. This is a subset of simple functions on E. It's a finite linear combination of measurable sets. You do have the added bonus that each of these sets are of finite measure, but often you don't really even care. A lot of times you really just want simple functions are dense in E, and you just don't care what these what these sets look like where you're taking the characteristic functions of them. You just care that they're a subset of E and they're measurable. And we'll put this to good use when we talk about absolute continuity. So these corollaries, again, just make proofs a little more efficient. So you don't have to repeat this little argument each time. All right, so long, take care, bye-bye.